Welcome to this lecture series in linear algebra. In this lecture, we'll look at the very important concepts of eigenvalues and eigenvectors. And let us recall just one simple thing. So if we have an endomorphism on a finite dimensional vector space V, then these things are equivalent. Injectivity, surjectivity, and bijectivity of T are equivalent, and bijectivity of T is same as, or it implies that T is invertible, and well, invertible as a set map, but not just as a set map. Its inverse is also linear. So that's what we mean by an isomorphism. Anyway, we have beaten this down 100 times. All right. Here are some problems for practice. And now let us get started. So fix an endomorphism on a vector space V, and again, every vector space that we consider will be finite dimensional unless otherwise mentioned. So we say that a scalar lambda, what have I written? We say that a vector V is an eigenvector of T if the image of V under T is in the span of the vector V. Seems like a strange thing to define, but let us try to look at it geometrically. So we have this vector, So we have this vector V, and we call this an eigenvector if after applying T, it does not change the line to which it belongs. And by line to which it belongs, we mean the span of V. When working with real vector spaces, this is geometrically meaningful, or you can visualize it, but for arbitrary fields, we can't visualize it very well. But that's the idea. If the line of alignment of a vector does not change after the application of a linear transform, we call the vector an eigenvector for the linear transform. All right. So before I make further comments, let me just quickly record that under this definition, 0 is always an eigenvector. So for any endomorphism T, 0 is an eigenvector. Now, some authors do not regard 0 as an eigenvector. It's a matter of convention. I will continue to regard it as an eigenvector. Okay. And let us note that this thing that's written over here, this is same as saying that span V is T invariant. Right? So equivalently, a vector V is an eigenvector of T if the span of the vector is T invariant. All right? Of course, eigenvectors are interesting only when they are non-zero, because the zero vector is kind of a trivial one. But that's the definition. And before we look at examples, let's look at a cousin notion, which is that of an eigenvalue. So let T be an endomorphism of a vector space V. We say that a scalar lambda, so capital F denotes the base field of the vector space. So we say that a scalar lambda is an eigenvalue of T if there is a non-zero vector, so if there exists a non-zero vector V such that TV is equal to lambda V. So what it is asking is that lambda is an eigenvalue if there is a non-zero vector whose scale, or rather whose image under T is the scale of V by lambda. So in the previous definition, we saw the definition of an eigenvector. An eigenvector is a vector which remains in its own span after the application of the transform. And eigenvalue is kind of asking what or the amount by which the vector got scaled. But anyway, I mean, the definitions I'm sure are clear. All right, so this is the definition of an eigenvalue, and this is very important. The non-zero-ness of this thing. If we scratch this out, then everything will be an eigenvalue, because T0 is lambda times 0, no matter what lambda you feed there. All right, so this is the notion of an eigenvalue, and let me make some remarks before we look at the example or an example to illustrate these notions. So the set of eigenvectors corresponding to lambda, and this is more like a definition. So if lambda is an eigenvalue of T, then the set of, or let me say, then a vector V is said to be an eigenvector corresponding to lambda if TV is equal to lambda V. So those vectors which witness the eigenvalue-ness of lambda, so to say. Of course, zero vector is also included in this. Okay, so note that this set is nothing but, the kernel of this transformation. Right, so the set of vectors, or the set of eigenvectors of T corresponding to a given eigenvalue lambda is precisely the set, and that's evident from the definition. Okay. So what else do I want to say here? I don't think there's anything at this point. So let's see the example that I have in mind. So we have the first example where we are given a linear map defined in this fashion. And we are asking what are the eigenvectors and eigenvalues of this map. So of course, 0 is an eigenvector. We want to talk about non-zero eigenvectors. Does this admit any non-zero eigenvectors? If you just visualize this, you will see that it does not admit any non-zero eigenvectors, because this map is just rotation of the plane by 90 degrees. So if this is our plane, if this is R2, then the map T, what it does is, it rotates the plane anticlockwise by 90 degrees. And therefore it cannot have a non-zero eigenvector, because it is not fixing the line spanned by any vector, because every line is getting rotated by 90 degrees. So that's, visually clear as to why this does not have any eigenvectors apart from the 0, 1, and therefore it does not have any eigenvalues. If it had an eigenvalue, it would have an eigenvector, non-zero eigenvector corresponding to it. So it does not have any eigenvalues either, but let's prove this formally. So let this be an eigenvector, and therefore there is some lambda such that this is the case. We just used the definition of an eigenvector. This being an eigenvector, meaning this thing is in the span of this thing, and therefore there is some lambda for which these two things are equal. Which implies, by definition of T, this is the case, which implies so what happened here? We have y, or rather minus y is lambda x, and hence y is minus lambda x, and we just substituted that here. So we will get this thing, which implies 1 plus lambda square times x is 0, and we are forced to have have that x is equal to 0 because lambda is a real number. Note that. I mean, there's nothing to note basically. Since this is in the span of this guy, lambda is a real number. We are working over a real vector space. So when we talk about spans, we're talking about things from the base field which scale the input vector. Okay, so x is 0, but that also implies that y is 0 because of you just combine this with that. If x is 0, then y is 0, and hence the only eigenvector is 0, and therefore no eigenvalues. So we just learned something. It is not necessary that an endomorphism has an eigenvalue. No eigenvalues, and hence the only eigenvector is 0. So that's what we showed. All right, wonderful. But what if we have the same definition, but this time we are having a bigger field in which we are working? So this is a complex vector space. The definition of T is quote unquote the same. But what about this? Does this have an eigenvalue or something? It does. So the same calculation. So fix some thing in C2, which is an eigenvector of T. So then the same calculation will tell us that minus y is lambda x and x is lambda y, which implies 1 plus lambda square x is 0. But this time, since lambda is possibly a complex number, right? Lambda is a complex number. It could be real also, but it is a complex number such that this is 0. So it's not necessary that x is 0. So there are some candidates for lambda. So lambda is either plus minus 1 or x is 0. But if x is 0, then y is also 0. Right? If x is 0, then y is also 0. So let us hunt for non-zero eigenvectors. So let this be non-zero. So here, let me amend the statement. We are hunting for non-zero eigenvectors. All right. So therefore, it forces, this equation, if x were 0, then y would also be 0, but we are starting with a non-zero vector. So this forces that this is the case. Fine. Now you can easily verify that, well, so what we have is minus y is plus minus I x, and you can easily check that 1 comma I and 1 comma minus I are eigenvectors corresponding to, I think it will flip. So with the minus sign, I think it will be like this, corresponding to minus I and I respectively. I hope I'm not making a sign mistake. Please check. So this corresponds to that and this corresponds to that. So this is the eigenvector, or an eigenvector, not the eigenvector, an eigenvector corresponding to this. And this is an eigenvector corresponding to that. So we need to take away a few things from this. When we were working over the real number field, we learned that there were no eigenvalues. So first takeaway is that it is not necessary for an endomorphism to have an eigenvalue. And second is that even if the endomorphism looks the same when you are working over a bigger thing, suddenly it can have new eigenvalues. So two very interesting things, we need to kind of let them sink in. Okay. So let's finish with, maybe I think this is the last thing for this lecture. So let's finish with the small lemma, if you will. So fix some endomorphism. And this orange thing I want to convert to white. Yeah, fine. So fix some endomorphism and some scalar lambda. then the following are equivalent. First is that lambda is an eigenvalue of t. Second is that this is not injective. And the remaining equivalences are just basic linear algebra. Non-injectivity is equivalent to non-surjectivity is equivalent to non-invertibility of any endomorphism, because we are working over a finite dimensional vector space. So let's just see this, and this is nothing. This is a matter of straightforward invocation of definition. So if lambda is an eigenvalue, then that's same as saying that there exists some non-zero vector in the vector space such that this is the case, which is equivalent to saying that t minus lambda I kills v, which means this is not injective. So yeah, this is not injective. And the rest is what we recalled in the beginning of the lecture. Okay? Very simple, but very useful. Sometimes you want to show that lambda is an eigenvalue. It might be easier to show that this has not full rank, right? It may seem like a very innocent thing, but it can be very useful. So 0 is an eigenvalue if and only if the endomorphism is not an isomorphism. I think, yeah, this is that corollary. So immediately from the previous proposition, this is invertible if and only if 0 is not an eigenvalue, or equivalently, 0 is an eigenvalue if and only if this is not invertible. Right. So the notion of an eigenvalue and eigenvector is very simple, but very central to linear algebra. It is one way to understand a linear endomorphism. If you know its eigenvalues, you have some purchase on the behavior of the endomorphism. All right, so let me stop here. As usual, like, comment, share, subscribe, and I will see you next time.